A thermal power station is a power station in which heat energy is converted to electricity. Typically, water is heated into steam, which is used to drive an electrical generator. After it passes through the turbine, the steam is condensed in a steam condenser and recycled to where it was heated. This is known as a Rankine cycle. The greatest variation in the design of thermal power stations is due to the different heat sources. Fossil fuel, nuclear energy, solar energy, biofuels, and waste incineration are all used. Certain thermal power stations are also designed to produce heat for industrial purposes, for district heating, or desalination of water, in addition to generating electrical power. Almost all coal-fired power stations, petroleum, nuclear, geothermal, solar thermal electric, and waste incineration plants, as well as all natural gas power stations are thermal. Natural gas is frequently burned in gas turbines as well as boilers. The waste heat from a gas turbine, in the form of hot exhaust gas, can be used to raise steam by passing this gas through a heat recovery steam generator. The steam is then used to drive a steam turbine in a combined cycle plant that improves overall efficiency. Power stations burning coal, fuel oil, or natural gas are often called fossil fuel power stations. Some biomass-fueled thermal power stations have appeared also. Non-nuclear thermal power stations, particularly fossil-fueled plants, which do not use cogeneration, are sometimes referred to as conventional power stations. Commercial electric utility power stations are usually constructed on a large scale and designed for continuous operation. Virtually all electric power stations use three-phase electrical generators to produce alternating current electric power at a frequency of 50 Hz or 60 Hz. Large companies or institutions may have their own power stations to supply heating or electricity to their facilities, especially if steam is created anyway for other purposes. Steam-driven power stations have been used to drive most ships in most of the 20th century. Shipboard power stations usually directly couple the turbine to the ship's propellers through gearboxes. Power stations in such ships also provide steam to smaller turbines driving electric generators to supply electricity. Nuclear marine propulsion is, with few exceptions, used only in naval vessels. There have been many turbo-electric ships in which a steam-driven turbine drives an electric generator which powers an electric motor for propulsion. Cogeneration plants, often called combined heat and power facilities, produce both electric power and heat for process heat or space heating, such as steam and hot water. The reciprocating steam engine has been used to produce mechanical power since the 18th century, with notable improvements being made by James Watt, when the first commercially developed central electrical power stations were established in 1882 at Pearl Street Station in New York and Holborn Viaduct Power Station in London. Reciprocating steam engines were used. The development of the steam turbine in 1884 provided larger and more efficient machine designs for central generating stations. By 1892, the turbine was considered a better alternative to reciprocating engines. Turbines offered higher speeds, more compact machinery, and stable speed regulation, allowing for parallel synchronous operation of generators on a common bus. After about 1905, turbines entirely replaced reciprocating engines in almost all large central power stations. The largest reciprocating engine generator sets ever built were completed in 1901 for the Manhattan Elevated Railway. Each of 17 units weighed about 500 tons and was rated 6,000 kilowatts. A contemporary turbine set of similar rating would have weighed about 20% as much. The energy efficiency of a conventional thermal power station is defined as saleable energy produced as a percent of the heating value of the fuel consumed. A simple cycle gas turbine achieves energy conversion efficiencies from 20 to 35%. Typical coal-based power plants operating at steam pressures of 170 bars and 570 degrees Celsius run at efficiency of 35 to 38%, with state-of-the-art fossil fuel plants at 46% efficiency. Combined cycle systems can reach higher values. As with all heat engines, Their efficiency is limited and governed by the laws of thermodynamics. The Carnot efficiency dictates that higher efficiencies can be attained by increasing the temperature of the steam. Subcritical pressure fossil fuel power stations can achieve 36 to 40% efficiency. Supercritical designs have efficiencies in the low to mid 40% range. With new ultracritical designs using pressures above 4,400 psi, there is no phase transition from water to steam, but only a gradual decrease in density. Currently, most nuclear power stations must operate below the temperatures and pressures that coal-fired plants do, in order to provide more conservative safety margins within the S.